and hello everyone. I am Dora Shazana Hamza. Today I will present the one which is set theory. What is set theory? Set theory is a branch of mathematics that studies set, which are a different collection of objects. Is one of the fundamental topics in mathematical logic and proof techniques because many mathematical concepts are built in one set. In this slide, I will explain the basic concept of a set in set theory. A set is a well-defined collection of distinct objects. This means the objects in a set theory are clearly defined and there are no repeated elements. The objects inside the set are called elements. For example, like A equals in set 1, 2, 3, 4. Since 2 is inside the set, we write 2 belongs to A or 2 elements to A. However, 5 is not in the set, so we write 5 not element to A. This table also shows some common symbols used in set theory, such as union, intersection, subset. These symbols help us describe relationships between different sets. This slide introduces the important set commonly used in set theory. For example, Z represents the set of integers and represents the natural numbers. W is the set of whole numbers. Q is the set of rational numbers. I is the set of irrational numbers, and R represents the set of real numbers. These symbols are widely used in mathematics. The example below shows that a set only contains distinct elements, so repeated numbers are counted only once. Therefore, set A has 4 elements and set B also has 4 elements. This is written as the cardinality of A equals 4 and the cardinality of B equals 4. This slide shows the main law of set theory that are used to simplify and solve set operations. Some of the most common laws are the identity law, commutative law, associative law, distributive law, and the De Morgan's law. This law helps us manipulate set correctly and make mathematical proof and problem solving easy. First, we apply De Morgan's law to the autoprime. This changes the union into an intercept and gives us double prime on box. Next, by the double complement law, double primes cancel out, leaving us with A union B intercept C intercept B. In the third step, we use the associative law to shift the brackets and remove the terms. Then we apply the commutative law inside the second bracket to swap C and B into B intersects C. We use the associative law once more to bring set B into the first bracket to be it together with B and B. Finally, by the association law, the entire first bracket simplified directly to just B. This leaves us with the final answer B intersects C. For this example 2, let's go through the solution step by step. First, we use the definition of subtraction to change the minus sign inside the first bracket as A intercept B prime. Next, we apply the Morgan's law and the double complement law. This contributes the autoprime changing the expression into A prime and B. In the third step, we notice that both brackets share a union B, so we apply the distributive law in reverse to factor it out, leaving us with A prime intersect A union B. Moving on by the inverse law, intersecting A prime, A result in an empty set which gives us empty set union B. Finally, by the identity law, any set union with an empty set remains itself. And that proof our expression equals B. That's all for me. Thank you.
Assalamualaikum. Today I will explain mathematical logic, specifically truth table and practical statement. This topic helps us understand how to decide if a statement is true or false and how to form by different statements. First, what is a truth table? A truth table is a simple chart that shows all possible true or false value of a logical statement. We use T for true and L for false. Let's start with a negation. Negation means the opposite of a statement. We write it as negation P. If statement P is true, then negation P is false. If P is false, then negation P is true. Example, let P, it is raining. Then negation P, it is not raining. Next is conjunction, written as P and Q. This statement is only true when both P and Q are true. Otherwise, it is false. Example: P, it is raining. Q, it is cold. P and Q, it is raining and it is cold. Now, this junction written as P or Q. This statement is false only when both P and Q are false. In all other cases, it is true. Example: P equals to Paris is the capital of Italy. Q is 2 plus 2 equals to 4. P or Q, Paris is the capital of Italy, or 2 plus 2 equals to 4. This is true because one part is true. Next is implication, also called a conditional statement, written as P plus Q. This means if P, then Q. P is hypothesis and Q is conclusion. Implication is false only when P is true and Q is false. All other cases are true. Example: she is happy. Q, she wins money. P implies Q. If she is happy, then she wins money. Now, be conditional, written as P if and only if Q. This statement is true only when P and Q have the same truth value, both true or both false. Example: P, she brings an umbrella. Q, it is raining. P only if Q, she brings an umbrella if and only if it is raining. For any implication, P implies Q, we have three related statements. 1. Converse. Q implies P. If Q, then P. 2. Contrapositive. Negation Q implies negation P. If not Q, then not P. 3. Inverse. Negation P implies negation Q. If not P, then not Q. Important rule: P implies Q is equal to is contrapositive. Negation Q implies negation P. Converse is equal to inverse. Q implies P equals to negation P implies negation Q. Example: original. If she is sick, then she takes medicine. P implies Q. Converse: if she takes medicine, then she is sick. Q implies P. Contrapositive: if she does not take medicine, then she is not sick. Negation Q implies negation P. Inverse: if she is not sick, then she does not take medicine. Negation P implies negation Q. Let's try a more complex example. Statement: if Ali is healthy, then he is brilliant and hardworking. P. Ali is healthy. Q. Ali is brilliant. R. Ali is hardworking. Original: P implies Q and R. Converse: Q and R implies P. If Ali is brilliant and hardworking, then he is healthy. Inverse: negation P implies negation Q or negation R. If Ali is not healthy, then he is not brilliant or not hardworking. Contrapositive: negation Q or negation R implies negation P. If Ali is not brilliant or not hardworking, then he is not healthy.
Assalamualaikum and hi everyone. Okay, my name is Siti Nabila and today I am going to explain one of your mathematical proof technique called the forward-backward method. Okay, for this method is used to prove statement in the form of if A then B. Okay, in this statement, A represents the hypothesis, which is the assumption, and that we know is true, while P represents is conclusion, which is what we want to prove. Now, let's look at how this method works. First, we have the forward process. Okay, in the forward process, we start from the hypothesis is A, then by apply mathematical definition, properties, or logical step. Okay, we move from A to A1, then A2 until we reach the conclusion of B. In other words, we begin with the information that is given and work forward to the result we want to prove. Next is the backward process. In the backward process, we start from the conclusion is B. We ask ourselves what condition must be true for B. Okay, then we work backward from B to B1, then B2 until we reach a statement that is related to the hypothesis of A. This approach helps us plan our proof before writing it formally. After that, we combine both the forward and backward process. Okay, you guys already know what is forward and backward process method. Okay, before looking for the example, let me tell you what important definition that I use in the example. Okay, an integer n is called even if and only if the remainder when n is divided by 2 is 0. In algebraic form, an even integer can be n equal to k, where k is integer. Now, let's look for the example. Okay, we want to prove the following statement. The following statement is, if m and n integers, then m plus n is even. First, we have to know the hypothesis and conclusion. Hypothesis is A. For this statement, A is m and n even integer. And for the conclusion is B, m plus n is even. After we know the hypothesis and the conclusion, A and B, after that, we have to know B1. Okay, B1 is m plus n equal to k, where k is integer. That is from the important definition that I explained before this. After we know B1, we need to know A1. By definition, we can write A1, m equal to A and n equal to B, where A and B integer. Now, A2, we substitute the expression into m plus n. So we can write m plus n equal to A plus 2B. Next, A3, we need to factor out the 2. This gives us m plus n equal to times A plus B. A4, let C equal A plus B. Since the sum of two integers also integer, C is integer. Therefore, m plus n equal to C. A4 is m plus n equal to C is equal and same with B1. The conclusion, we successfully prove that if m and n even integer, then m plus n is also even. In the conclusion, the forward-backward method is useful proof technique that helps us organize our mathematical reasoning. The forward process starts from the hypothesis and moves the conclusion. The backward process starts from the conclusion and work backward the hypothesis. When both processes connect, the proof became clear and complete.
Assalamualaikum. In this presentation, we will explore the structure of logical arguments, the rules of inference that govern valid reasoning, and walk through step-by-step proof to demonstrate how we can verify if a conclusion logically follows from a given set of premises. Let's begin by defining what an argument is. Before we can prove anything, we must understand the structure of a logical argument. First, an argument is defined as a list of given statements called premises, followed by a final statement known as the conclusion. As we can see at the slide, formally we group all our premises P1, P2 up to Pn as our hypothesis. And below the line, we write the conclusion, therefore Q. To evaluate whether this conclusion follows logically, we set up a conditional implication. We join all of our premises together using the AND operator to form a single compound antecedence, which then points to our conclusion Q. An argument is declared valid if and only if whenever each of the individual premises in our hypothesis is true, the conclusion Q is guaranteed to be true as well. Therefore, one of the primary ways to prove the validity of an argument is by showing that this implication is a tautology, meaning it is true under all possible truth values. Now, let's explore the established logical templates, the rules of inference. To build a formal proof, we use standard rules of inference. They are logically valid argument forms that act as template for our reasoning. There are 7 types of primary rules. First, we have modus ponens, or the law of detachment. Second is the law of syllogism. Third is modus tollens. Fourth, the rule of conjunction. Fifth, rule of disjunction with syllogism. Sixth is the rule of conjunctive simplification. Lastly, we have the rule of disjunctive amplification, sometimes called addition. Now that we have our toolkit ready, let's apply these rules to some practical examples. Let's look at a concrete problem. We want to prove the validity of this argument. If Amin is guilty, then Amin have a motive and it was a dark night. Amin does not have a motive, therefore Amin is not guilty. We begin by defining our proposition variables. Let's P represent Amin is guilty, Q represent Amin have a motive, and R represent it was a dark night. This translates our premise into the formal system you see in the top right box. Premise 1, P implies Q and R. Premise 2 is negation Q, and therefore negation P. Let's walk through the proof step by step. We start with our first premise, the conditional statement P implies Q and R. We write down our second premise, which is negation Q. Using the rule of disjunctive amplification or addition, on step 2, we can write negation Q or negation R. By applying De Morgan's law to step 3, we can rewrite the expression as the negation of a conjunction, which is negation Q and R. Finally, we compare step 1, P implies Q and R, and step P, which is negation Q and R, because the consequence Q and R is false. We can use modus tollens to conclude that the antecedents P must also be false, giving us negation P. Since we reach our target conclusion using valid rules, the argument is successfully proven valid. My next example, let's look at a slightly more complex argument involving 4 variables. If Sarah is winning, she isn't stressed and isn't losing focus. She is either winning or having bad luck, but she is stressed. Therefore, she is having bad luck. Let's define our variables. P is Sarah is winning. Q, Sarah is stressed. R, Sarah is losing focus. S, Sarah having bad luck. This given us 3 premises, which is premise 1, P implies negation Q and negation R. Premise 2, P or S. Premise 3, Q. And therefore S. Here is how the proof unfolds. Step 1, 2 and 3 are simply listening our given premises. In step 4, we take premise 3, which is Q, and apply disjunctive amplification to get Q or R. In step 5, we rewrite the consequence of premise 1 using De Morgan's law. The expression negation Q and negation R is logically equivalent to negation Q or R. So, our conditional statement becomes P implies negation Q or R. In step 6, we compare step 5 and step 4. Step 4 tells us Q or R is true, which means it's negation. Negation Q or R is false. Applying modus tollens to step 5, we can conclude that the antecedents P must be false, written as negation P. Finally, in step 7, we look at premise 2, which is P or S, which states that Sarah is either winning or having bad luck. Since step 6 proves she is not winning, which is negation P, we use disjunctive syllogism to conclude that she must be having bad luck. S, which is S. This completes our proof. The argument is valid. In conclusion, the rules of inference provide a powerful step-by-step method to prove an argument is valid without using tedious truth tables. By translating ordinary statements into formal symbols, which is P, Q, R, or S, we can systematically show that the combination of our premises logically false the conclusion to be true, creating a definitive tautology.